Hello, and welcome back to my YouTube channel. My name is Professor Gavala, and today I will be doing the second installment for the course, which in most universities is referred to as EE 220. And today, the main things we'll be talking about are electric charge and current. We will be talking about voltage, and we'll be talking about ground, where these three things here, current, voltage, and ground, are used a lot by electrical engineers, but I feel like most people don't know what they are. As a result, I will explain with easy to understand examples on what each of these things are and how they can be interpreted easily. So, to begin, we give credit to a French scientist called Charles Augustin de Coulomb, where he was the one who was a pioneer when it came to defining charge, which is why we name a charge by him, his last name, Coulomb's. And he gave us four definitions that said that the first thing is a charge can be positive, a charge can be positive or negative. The second thing is the fundamental quantity of a charge is that of a single electron or proton denoted by E. And then the third thing is the law of conservation of charge. That says that the net charge, the net charge in your system or in an enclosed region can neither be created or destroyed. And this is similar to energy, right? Energy can neither be created nor destroyed. The same thing with the net charge in an enclosed system. And the fourth thing is this is similar to what happens when you have magnets next to each other, but two charges repel one another, and two charges of opposite polarities attract. So essentially, if I have a minus and a minus, the direction that they want to go is away from each other. And if I have a plus and a minus, the direction they want to go is towards one another. So we can define the unit of charge as E is equals to 1.6 times 10 to the negative 19 coulombs. And this is also called Q, where a charge on a single proton, QP, is equals to E, and the charge on a single electron is equals to minus E. So now let's define what is electric current. And in order to define electric current, we really need to understand that this charge is a single electron, and that is defined as 1.6 times 10 to the negative 19 coulombs. And now, electric current is the action by charge attracting or repelling each other, causing the movement of charge from one location to another. So that means that electric current, if I have a wire, and I have an electron here, an electron here, what this means is current is electrons moving in that median or that space where this is the electron. And I'll explicitly write out the definition just so there's no confusion. So we say the action by charge attracting or repelling each other, causing the movement of charge from one location to another. So just the movement of this electron, right? So anything that causes this electron, we don't know what that thing is yet, but just the movement of this electron in a wire or a space or a median, that is defined as electric current. Where in a schematic, we can zoom this movement of electrons into something like this, where this wire can be zoomed in here. And it's a chunk of this wire. Where we have that this is I, this is a resistor R, and this is V. And we will discuss more about V and resistance. But for now, everyone should know what electric current is. And it should be noted that the direction of electric current I is defined to be the same as the direction of flow that positive charge would flow, which is opposite to the direction of flow of electrons. And what that note means is that, conventionally speaking, we identify I to be flowing from voltage plus to voltage minus, which is E, but the electrons actually flow, right? Again, our denotation for electrons actually flow in this direction. But standards, in terms of standards, we defined I to equal to E, and it flows in the direction of plus to minus. And so we can now define electric current in terms of an equation. And electric current, let me change colors. It's defined as the time rate of transfer of electric charge across a specific cross section. And we kind of saw that here in this picture, but to be more formal, the equation is I is equals to the change in charge over a given time. So dq over dt, again, this is the amount of charge, and over an infinite small time duration. And the units are amperes. And it's actually what these look like in different domains are. This is in DC. So this is where you capital I, this is direct current. And this is what you look for in like your batteries or your power supplies. Another type of current is AC, alternating current, and it's depicted by a little I of t, and this is varying as time goes on. And this is household systems or an oscilloscope. So now let's take an example where that we have a graph that looks like this, and this is our current. This is T. Actually, let me redraw that current. This is current. This is I of T. This is 6 amps. So we can depict this graph. We can depict this graph as I of T is equals to from 0 to 6e to the minus 0.2 t for t less than 0 and for t greater or equal to 0. So essentially, what's happening here is that for t less than 0 over here, my current is 0. And for t greater than 0, or greater or equal to 0, my t is this given um, exponential function, where simply put I of 0 is equals to 6e to the minus 0.2 times 0, which is 6e to the 0, which is 6 times 1, which is equal to 6. And what you can do is, given different points in t, let's say 1, 2, which this is normally milliseconds, you can get the different values of your current. Now, the problem asks us to develop an expression for the cumulative charge QT that has been transferred past the cross section up to a time t. So now all we need to do is we need to know our equation, which is sorry, we need to know our fundamental equation, which says I is equals to dq over dt. Then that would mean that q or dq is equals to I times dt. Or in order to get rid of the d's, we can integrate from negative infinity to t of dq is equals to negative infinity to t dt. And essentially this is qt minus q negative infinity, which is equals to negative infinity t I dt. And we can see here that we can note that q of negative infinity is equals to 0, simply because at times 0 to negative infinity, there's no current flowing. So that means that there's no charge flowing as well. So that's equal to 0. So what we can simplify and say now is that we can have a generalized equation that says q of t is equals to negative infinity to t I of dt. And this is for I of t equals to 0 for I less than 0. We can say that in this situation, for I of t equals to 0 for I less than 0, we don't need this infinity. So that means q of t is equals to 0 to t I of dt. And now we could start plugging and chugging, where this is q of t is equals to 0 to t 6e to the minus 0.2 t dt, which is equals to negative 6 0.2 e minus 0.2t from 0 to t. This is just basically calculus. Um, and since this is not a calc class, we'll just give the answer, which is 30, 1 minus e to the negative 0.2t. Then this is your answer. Where we can also write this as minus 30e to the negative 0.2t plus 30. And all you do to get this is plug in t. Sorry, you want to plug in t and then subtract that from when you plug in 0, right? And you should get this and this. So we can now say that q of 0, so this is q of t, we can plug in 0, we get 0, and q of plus infinity is equals to 30 coulombs. So when you plug in infinity into t here, this equation becomes 0. So you're left with 30. And what we can generalize this to is to say that as t goes on, what is q of t? We can generalize this and say that q of t looks something like that, where this, it saturates at 30 coulombs. Another example we could take is, given that you're given a charge for t less than 0 and for t greater or equal to 0, and this is in coulombs, they ask you to find the current. Again, we use our fundamental equation. I is equals to the change in q over the change in t, which is d5 times t e to the negative 0.1 t over dt, which we get 5e to the negative 0.1 t minus 0.5 te to the negative 0.1 t. And again, this is just derivative using an exponent. Or we can rewrite this as 5 minus 0.5 t, and then pull out the e to the 0.1 t, and this is amps. So this is our general equation. And what we can do now is we can say I of 0 is equals to 5 minus 0.5 times 0 times 1, which is equals to 5 amps. So at 5, so at q of 0 is equals to 0, we actually get I of 0 is equals to 5 amps. Next, the question asks us to determine the instance at where qt is a maximum and the corresponding value of qt we need to find. So find the instance where qt is a maximum and the corresponding value of q. So maybe pause the video and see if you can figure that out. But now I'll try and show you how to solve it. And the solution is maximum is the derivative equals to 0. So essentially, we need to find dq over dt, and we already did that, which was 5 minus 5, sorry, 0.5 t e to the negative 0.1 t. And so when we equate this to 0, we get that we get a 5 minus 0.5 t is equals to 0, which is this part. And we need to say 5 is equals to 0.5 t. That means that t is equals to 5 over 0.5 or 10 seconds. Now, or if you remember from algebra, it also means that e to the minus 0.1 t can also equal to 0. So that means that t is equals to infinity. That's when that happens. So now, which one is the maximum and which one is the minimum? So is 10 seconds the maximum where the current reaches maximum, or is it infinity where it reaches its maximum? And what we can do to find that is maybe actually before we do that, pause the video and see which one is a maximum, which one's a minimum. Try and solve for that. And so the answer is you would simply plug this into your equation for Q of t. So basically Q of 10 is equals to 5 times 10 e to the minus 0.1 times 10, which is equals to 18.4 coulombs. And Q of infinity is equals to 5 times infinity e to the minus infinity, which is equals to 0. So that means that if I have a graph and I want to graph what Q is doing in terms of what this Q here is doing, we could say T and we could say Q of T. And then we could say that there's a maximum of 18 coulombs at 10 seconds. At 10 seconds, so this is a point. And then as it reaches infinity, it goes down towards 0. And at 0, before 0, it's 0. And after 0, it rises up to 18. So this is kind of what our current is doing. Sorry, our charge is doing. So I hope this concept of charge and current makes sense. So essentially, to recap, whenever you want to find the charge given a current, you need to take the integral as shown here. And whenever you want to do the reverse, which is find current given charge, you need to take the derivative. And this is why things like all the calculus, Calc 1, Calc 2, and Calc 3 were very, very important before starting this electrical engineering course. So next, we will move on to what's called a voltage. And this is a very important concept. Essentially, voltage is used everywhere in electrical engineering. And the formal definition is the voltage VAB between location A and location B is the ratio of dW and dQ, where dW is the energy in joules, J, required to move a positive charge dq from B to A, or a negative charge from A to B. And this is also called the potential difference. And the potential difference, VAB, is equals to dW over dQ, and it's measured in volts. And I always like to give credit to inventors, and it's named volt after uh, Alessandro Volta, and he was the one who pioneered this section of engineering, or this area of engineering. And essentially, what that means is that if I have a certain area, and you can think about this as even a cabin or an enclosed area, and there's a lot of molecules in that area, so pressure. And basically, you can think about this as electrons, or you can think about this as atoms in a room or in a bin. Now, what all voltage is the pressure here might be greater than the atmospheric pressure outside. So this is outside. And what we do is we just have a tool that measures what is the pressure here, what is P inside, and what's the atmospheric pressure P outside. And P difference is equals to P inside minus P outside, where the P outside is probably smaller, right? Atmospheric pressure outside is probably smaller than the inside. But essentially, in a wire now, what happens in engineering is when we have a wire and there's a battery attached to that wire, we pressurize the battery with a whole bunch of electrons, and we have another area where it's called ground, but we'll define ground in a little bit, that doesn't have that much electrons. Again, I'm writing this in very simple terms, but all we do is now the difference V, so let's say this is A and this is B, VAB is equals to VA minus VB. So that's all voltage is. It's just a difference in voltage, or a difference in pressure of electrons enclosed in a certain area. And what happens is if you have A, which is actually, this is how batteries work, they want to go, because remember now, opposite charges attract. So these plus charges want to go and meet with these minus charges. And essentially, what we do as engineers is we put a component here. And this component could be your electric stove at home, or it could be a light bulb, an incandescent light bulb. And when the electrons pass through these mediums, they release heat, or they release photons. And those photons flow in a wavelength that give light to our eyes. Or they release heat, and we could put it on a metal surface, and we could put a pot on there and heat up the pot. That's all we do. Well, I shouldn't say that's all we do, but that's one of the main things that we do as electrical engineers, is we just pass these electrons through what you consider a load. That's what you consider a load. We're loading up a device, and the device is either releasing something into the surface, and now everything else within that is to make it more efficient, more smaller, for for the applications that are needed. But essentially, if I were to take a probe and measure my voltage here, the amount of electrons here, I might get 9. And if I measure the amount of electrons here, I might get 2. So that means that there is a voltage rise, of a rise from V to A of 7 volts. So I hope this concept of voltage makes sense. Again, simply put, it's just measuring 2 points and figuring out the pressure or the amount of electrons that are pressurized in that area. Now, in order to continue, we have to define what's called ground. And ground, it's also a misconception. Now, it's also a misconception in electrical engineering in terms of we always consider ground to be 0 volts in a schematic, which is not necessarily the case. The definition of ground is a reference point for which all other voltages can be calculated, right? And for convenience, this is typically the lowest voltage in the system. So ground can be any voltage. So in this system here, this can be my ground. This can be my ground, but it's 2 volts. But compared to everywhere else in the system, where this is 9 volts, this is 9 volts, it's the lowest voltage. So again, we define some location to be real ground from which all other voltages can be calculated. And for convenience, this is the lowest voltage in the system, where the ground for a mobile system, such as your phone or your laptop, there's a chassis or metal structure, or even your car, a metal structure called the chassis ground. And in a building like your work office, in the building, there's a physical area when the architectures or the civil engineers are building these buildings, there's a physical rod or physical rods in the dirt near the structure. And again, they just hold, we call this earth ground. And all it is they just hold a lower voltage or lower voltage or lower pressurized area when compared to everywhere else in the building. And just a quick note about ground, I made note of this, but we can spell it out as GND for short. And you're going to see 2 notations for it. One that looks like this and one that looks like that. Actually, there's a lot of different symbols you could see, but then another one could look like this, where this is that chassis ground in your mobile devices. This represents more of a signal ground, right? And this one represents an earth ground. So just a few more things and we'll wrap up for this lecture. But I want to talk about in your schematics or in your circuits, how do you measure volts and how do you measure current? So given a circuit that looks like this, where this is Vs or V source plus minus, we can put, to measure the voltage across plus or minus Vr, this is resistor R, to measure the voltage across this, what we do is we have this device called a voltmeter, right? And a voltmeter has little to no resistance. And I'll explain a little bit more on that but we take one of the pins and put it here, and we take another one of the pins and we put it here. Let's say that this is our ground. This is our lowest voltage in our circuit. So, and it depicts the voltage here. This is the voltmeter. This is the voltmeter. And actually, I made a mistake. The voltmeter has a high resistance, right? So if I can do something here, if I can just take this section and then say that a current flows through here. If my current flows in like so, and there's two paths it can take. A path where we have a 1 megabyte resistor or a 10 kilo ohm resistor. Most of the current will flow through here. So essentially, we want the maximum current to flow. We want the maximum current to flow through the 10K resistor. Again, I think I made mention to this in the first lecture. It's like you're going to work and there's no traffic. There's the least amount of resistance on the side street versus a lot of traffic on the highway. You're going to take the side streets. So that's what the electrons do here. So, and again, this is something that goes into designing voltmeters is there will be some currents, there will be some like a very, very, very small amount of current that goes through your 1 mega ohm resistor. But again, it's negligible compared to the current that flows to the resistor. And what we do now is we measure that voltage. We measure that voltage through this parallel configuration, because since this is in parallel, the voltage that drops through here is the same voltage that would drop through the 1 mega ohm. And again, the way to prove that based on voltage difference is we defined the voltage difference to be 2 points, where the 10 kilo ohm and the 1 mega ohm resistor share a VA and a VB. So that means that their voltage difference VAB is equals to VA minus VB, where we're still making the 10 kilo ohm take the most current, but we're measuring the same amount of voltage. So I hope this concept makes sense on how to measure voltage in your schematic. A real life example of this is if you have your battery in your car. Looks something like this. There's a plus sticking out. There's the minus. You can take a voltmeter, which you can buy online for like $10, and put the red lead here, and you could put the black lead here and measure your voltage, and you would get the charge of your battery. Okay. So now how do we measure currents? Current is the opposite of voltage in the sense that in order to measure our current, we want to attach what's called an amp meter in series with our circuit. This is the amp meter in series with our circuit. And the idea here is the amp meter actually has little to no currents, little to no resistance, little to no resistance. So that means that whatever, this is Vs, this is R, whatever current is flowing through here will flow through the amp meter, and no voltage will drop through the amp meter. So that means no heat is dissipated, right? So again, in this sense, imagine if we have a resistor that's 10 mega ohms, and we have a resistor that's only like 1 ohm, The for the current to go through here, think about it like this: when you're going through traffic and there's a huge amount of people in line, you're and it's hot outside, you're sweating a lot, you're dissipating heat. So the electrons also kind of do something like that. They they waste a lot of energy passing through this 10 mega ohms versus this 1 ohm resistor, which they just pass through. And what we can do is we can devise a method of measuring the current that um, passes through. So essentially, an ammeter is basically, you can think about it as a wire just passes through here, and we measure our currents because the current through all this in series is the same. So again, that's kind of how you measure current, and maybe I can give a quick example here, or maybe I'll give a quick example for you to try, and you can see if you have it right. I'm gonna write it off the recording, the answers. So essentially, I'm gonna write out the problem. I'm gonna write out, this is the problem, R1, R2, right? This is the problem, and I want you to find out. I want you to draw how to measure your voltage and measure your currents in terms of using an ammeter and using a voltmeter. I'm going to pause the video. I want you to pause the video as well. And when I play it, you're going to see my schematic here. So here we have it, right? So basically, and again, I didn't specify, but either one would have worked if you wanted to find the voltage through R1 or R2. So this is how you would have drawn it, where terminal A is here and terminal B is here. And for current, you would just connect it in series because the current is the same throughout this entire loop. So I hope you got that right. That's also a big interview question. So you can expect a question like this asked in an interview, how you would configure a voltmeter or an ammeter in a circuit diagram like this. All right. So with that being said, we're gonna end the lecture there. Again, in this section, we talked about charge, current, voltage, and ground. And we also learned how to measure voltage and amps in a circuit. Where next time we will talk about switches. So switches is a big thing. It looks kind of like that. And this is basically your off position and your on position. Where in your household, this is what your switch does. It literally just turns it off and turns it back on with like a fan. Um, we'll talk about power. Power is extremely important. We'll talk about how essentially your load resistor, your current, sorry, your load resistor, your current, and your voltage all play a big part when measuring measuring power. And then we'll talk about what's called and dependent dependent sources, where these sources can be a voltage source or a current source. And this is also a very, very important concept. So please stay tuned for that. Again, like, subscribe, comment if you are facing any difficulties that you want me to respond to. Please share my content and let me know if there's anything I can do to improve on what I'm putting out here. So thank you and have a good one.